During an around-the-world flight attempt in 1937, Amelia Earhart and her expert navigator Fred Noonan vanished in the South Pacific. Because their plane had limited range, they were forced to use this tiny and remote island called Howland Island as a refueling stop. Earhart's flight plan listed the island's coordinates as 0 degrees 49 minutes north latitude and 176 degrees 38 minutes west longitude. But the actual lat-long coordinates are 0 degrees 48 minutes north and 176 degrees and 38 minutes west. Traveling off course in the dark, with their view hampered by clouds, they overflew and missed landmarks that could have helped them fix their position. Additionally, neither knew Morse code, which they could have used to communicate with Navy ships. The plane was poorly outfitted for navigation and long-range communication, and neither Earhart nor Noonan was well trained on the radio equipment they did have. Their eastbound route led them into headwinds, and this cost them fuel. Amelia Earhart and Fred Noonan did not complete their round-trip journey. Although many theories exist regarding their disappearance, none of these have been proven. Many scientists believe that they crashed the plane and sank into the Pacific Ocean. Earhart's story illustrates that errors on maps or errors made when reading a map can have drastic effects. Your ability to read topographic maps is not only essential for geologic studies, but it can also help you safely plan a hike or wisely develop land. So what is a map? This is probably a silly question. Chances are you've used a map, or more likely a mapping app on your phone to find a new restaurant or navigate a new city. But just in case, maps are diagrammatic representations of an area of land or sea as views from directly overhead. In this case, we can see a map of the Arctic and the Antarctic regions. There are millions of maps in use today, but most geologists are interested in two types of maps: geologic maps over here and topographic maps over here. Geologic maps show the distribution of rock types or sediments at the Earth's surface. In these maps, each one of these different colors represents a different rock or sediment type. Topographic maps, on the other hand, show variation in elevation across the map area using what are called contour lines. So contour lines connect points of equal elevation, meaning that every point along this line is at the exact same elevation. If you were to walk across this line or along this line, you would be at the same elevation all the way along it. And the elevation is listed for each line in this case. It's probably pretty clear that a lot of information can be presented on a map. But regardless of type, all maps should have a few basic components. So first, every single map should have a title, and that's listed up here. A title tells you what this map is about. It should be short but descriptive. In this case, we're looking at a topographic map of the island of Hawaii, so this would be the Big Island. Every map should also have a north arrow, and the north arrow tells you how the map is oriented. If there is no north arrow, then we can assume that the top of the map is oriented north. Every map should also have a scale. A scale tells you the proportion of this map to real life. In this case, the scale bar tells us that this length of line is equal to 40 kilometers in real life. Every map should also have a legend or a key, and the legend will tell you what every single line or symbol or color on the map represents in real life. This is a very simple map, so we just have a simple key that tells us that the contour interval is 1,000 feet, meaning that the difference in elevation between each one of these contour lines is exactly 1,000 feet. The last thing that every map should have is a date, and a date will tell you when this map was published. And that will be important because it tells you if your map is out of date. This map doesn't have a publication date, which for us is going to be a red flag. This is a more complex map, complete with a full legend. This legend tells us that brown solid lines on the map represent topographic contours. They basically tell us the elevation, and some of those topographic contours are labeled with the elevation in feet. The blue dashed and dotted lines tell us where we have streams or rivers, and we also see two separate symbols for railways. So these are dashed lines either in black or in purple. This is an old convention telling us that purple lines have been constructed since the last publication or last edition of the map was released. It's not commonly used anymore, but you may come across it in some maps of the US. We also have large areas that are colored in green to represent vegetated areas. And we also have large areas shaded in blue to represent bodies of water. So these items are really important because if we didn't know what each of these things represented, we wouldn't know what this map is telling us. We could assume that these green areas represent vegetated areas, or we could assume that they represent UFO landing sites or areas inhabited only by naked mole rats, for example. So legends are really important. Most maps also have a reference system, and this is some kind of grid overlaid on the map that allows you to pinpoint a location. As we learned with Amelia Earhart, getting those coordinates wrong can have dire consequences. And you could argue that reading and understanding maps is less of a critical skill today, given all the navigation software that we have embedded into our phones. But many remote places on Earth don't have Wi-Fi. In fact, even if you're just heading up a mountain on the fringes of Canmore or maybe in Kananaskis, it's likely that you're going to lose Wi-Fi coverage. GPS units, independent GPS units are definitely better, but they still require electricity. What if you have no power? So my suggestion, of course, is if you want to go exploring the depths of the Amazon forest or trek across the Great White North, you definitely still need to know how to read a map. As I mentioned earlier, the publication date is missing from these maps, and you may be wondering why that's a big deal. Let's imagine that you've been hired to build some new infrastructure on the big island of Hawaii, and you are basing your plan on a 2012 map. But the area you were planning to build on had been affected by the 2018 eruption, which changed the shape and the elevation of the land. This could have major impacts on your design. It could change the direction in which water flows. It could block potentially the view that you had intended for your building, and it may even make the land unsafe to build on. So clearly, it's really important to use an up-to-date map when planning any infrastructure or hikes. One of the most important features on a topographic map is the scale. This is often represented as a bar of defined length with an indication of how much distance that bar represents in real life. The length of the scale bar on this treasure map is 5 centimeters long. The scale bar tells us that 5 centimeters on the map is equal to 10 kilometers in real life. Any distance measured from the map is called the map distance. This scale bar is used to convert map distance to a distance in real life. So if you were to travel a distance equal to 5 centimeters on the map, you would actually be traveling 10 kilometers in real life. Alternatively, the map scale can be expressed as a ratio. To do this, we first need to convert all lengths to the same units. We already know that 5 centimeters on the map is equal to 10 kilometers in real life. We also know that 10 kilometers is equal to 1 million centimeters. Therefore, 5 centimeters on the map is equal to 1 million centimeters in real life. And this is equivalent to a ratio of 5 to 1 million. But we're not quite done. The next step is to reduce the ratio. So in this case, we're going to divide both sides of the ratio by 5. The point here is to indicate how many units in real life are represented by a single unit on the map. Therefore, the map ratio is 1 to 200,000. Now, importantly, you'll note that there are no units here. This means that 1 centimeter on the map is equal to 200,000 centimeters in real life. It also means that 1 inch on the map equals 200,000 inches in real life. Or it means that 1 furlong on the map is equal to 200,000 furlongs in real life. This is a ratio, so it works no matter which units you want to use.